OCR Statistics, Discrete Random Variables 2, Binomial and Poisson Distributions. This is video 2.3 on the Poisson distribution as a model. Many experimental situations occur in which we observe the count of events within a set unit of time or area, volume or length. For example, we may want to record the number of births on a given day in a hospital. This would enable us to have an average birth rate per day and use this to make predictions about the future. Here are some other examples of events where we are counting in a certain time or space. We've already looked at the number of births at a hospital on a particular day. Here we're counting the number of cases of a particular disease in a different town. This one is about counting the number of mutations in a set-sized region of a chromosome. And finally, we have the number of particles emitted by a radioactive source in a given time. So they're all about counting in certain time or space. The Poisson distribution is a discrete probability distribution for the counting of events that occur randomly in given time or space. It was first proposed by the French mathematician Simeon Poisson, and he used it to represent the pattern of wrongful convictions per year. This distribution can be used to model the probability of outcomes in situations like this. This is the formula that is available in your formula booklet. Proof of this formula is beyond the scope of this course, but in future videos we will show you how to use it. Notice here that x can only take positive integer values. It's not possible to have a negative value. If you think about counting the number of births, it doesn't make sense to have negatives. Lambda is what we call our parameter, and we will explore more about this later. If we can model something using the Poisson distribution, we can write this. Many of you will have already come across the constant E in pure maths. It is a very useful and important number that is used in maths, statistics, calculus. The list is endless. We're now going to have a look at the shape of the Poisson distribution, and the easiest way to do this is to look at GeoGebra. Okay, we're now in GeoGebra looking at the Poisson distribution. So we've selected Poisson. Notice that GeoGebra uses mu here rather than lambda, so just be aware of that. I've set, well, I'll call it lambda just to avoid confusion. I've set lambda to be equal to 1. If you were thinking about that as a birth rate, that would represent 1 birth per day. And here you can see that the distribution has got a really long tail. It actually goes on forever, but we just can't see it, and the probabilities are so small. If we change our parameter, so say for example we increased it to 5, you can see here that it does become a little bit more symmetrical. Still got this very long tail here. If we increase it again, let's try 10. You can see again it's starting to become more symmetrical. And what about 100? So you can see here we're actually starting to get something that's looking a lot more like the normal distribution. We're now going to look at the conditions that need to be satisfied for x to be modelled as a Poisson distribution. Firstly, our events must occur at random, and they must be independent of each other. So one event does not affect the other event happening. The average number of events in the given interval, which is what we're calling lambda, is fixed and finite, and this rate is proportional to the interval. And what that really means is if our rate is 3 births per day, we would assume that there would be 6 births in 2 days. And finally, that events occur singly, or just one at a time. Now let's look at some examples and see whether we could try and model them with a Poisson distribution. So firstly, if we looked at the number of insurance claims made in a given month. Now clearly here we are counting in a given time period, but is it appropriate to assume that their rate is proportional? Because surely in winter we have a lot more accidents than we do in other times of the year. This one is looking at the number of cars passing in a 10-minute period, but might roadworks affect whether these cars would arrive singly? So we may have to make certain assumptions to use the Poisson distribution, but it may be the best fit. This was video 2.3 on the Poisson distribution as a model. The next one is 2.4 on calculating probabilities using the Poisson distribution.